All right, AP Chemistry folks, wanted to go over that last page on the packet that kind of reviews the molecular geometry and hybridization stuff. I think that a lot of questions are coming up because students are making things more difficult than they are. So I want to just highlight a few of these. I'm not going to go over every single one of these answers. However, I will put the answer key on Classroom so that you can check your work. I want to look at carbon dioxide and water first here along the left-hand side to show you some stuff with molecular geometry and with hybridization. First of all, in order to be able to do molecular geometry or hybridization, you have to be able to write the Lewis structures correctly. So if you can't draw Lewis structures correctly, that's a problem. And that is something that I'm not going to be going over here on this video. You can go back to the other work that we did in class and video previously for that information. So notice though that when we look at carbon dioxide and water, they both look very similar. We have a central atom with two things attached. A central atom with two things attached. Now when I say things, I'm talking about bonded atoms. The difference here is that water has these additional lone pairs on that oxygen molecule. And so this changes the molecular geometry. Linear for carbon dioxide, bent for the water. Remember that everything has electron clouds and electrons are negative. Therefore, everything is trying to get as far away from each other as they possibly can. To do this, when we have two things attached, it becomes linear. If we have a situation here, we have the lone pairs, it becomes bent. Now when we look at the hybridization, notice that these are not asking you to show the hybridization process with electron configurations. That's a different part that I'll show you in just a couple minutes. This is just asking you to identify the hybridization. So we count up the number of things attached to the central atom, 1, 2, and we show the hybridization of how that works. Notice or remember that the exponents add up to the number of things attached to the central atom. So we don't show 1, so there's a 1 here and a 1 there. That totals 2. There's 2 things attached. So that's the sp hybridization. We have 2 sigma bonds. Sigma bonds are always going to be the first bonds that happen, or single bonds. And pi bonds are the double bonds, the second bond that happens. It does not matter which of these two bonds you mark sigma and pi, but there's a sigma on this side and a pi on this side, and same thing on this side of the carbon. Where water, we only have single bonds, so those are going to be our sigma bonds, and then we have no pi bonds because there's no double bonds, and the sp3 hybridization comes from 1, 2, 3, 4 things attached. sp3. Now if we look at the phosphate ion and the sulfur tetrafluoride, we see a similar situation. We have 4 bonded things attached, but this sulfur has that lone pair of electrons, so that's going to change the geometry as well as the hybridization. Here we have sp3 hybridized, 4 sigma, 1 pi. Here we don't have any pi bonds, just the 4 sigma, but it turns out to be sp3d hybridized instead of sp3. This guy here, the phosphate tetrahedral, where this guy is going to be distorted tetrahedron because of that extra lone pair. The other one I want to show you is this nitrogen molecule. Nitrogen is a diatomic molecule, and so it does not have a molecular geometry. In order to have a molecular geometry, you need to have a central atom with at least two bonded things on it. This only has 1 bonded thing and a lone pair. Because of that lone pair, though, it's sp hybridized, 1 sigma bond, and then 2 pi bonds. Notice that I added the lone pair on this nitrogen, but lone pairs around these oxygens or up here in the fluorines I do not include. That's because they are not necessary in order to tell the information we need about the molecular geometry and the hybridization. Lone pairs on the central atom are required, or in this case, on one of the diatomic molecules. Now, you will be asked on the test to show the hybridization process. So I have 7 different examples that I want to look at here. It's kind of crowded in here, so I'm going to see if I can break it down for you so you don't get lost. These 3 are going to be really straightforward. These 4 are going to have little extra pieces in it that we need to make sure that we're aware of. So we have the Lewis structure still is required to be able to tell what kind of hybridization it goes through. So still draw that. Then we use the electron configuration to show the hybridization process. So we have 3 valence electrons. Remember that valence bond theory is built on the idea that unpaired electrons are what do the bonding. So we have a paired set of electrons here, one unpaired. According to valence bond theory, this guy should only be able to do 1 bond. However, we know it doesn't. It has 3 bonds based on the different kind of chemical compounds we can create with boron. So we have to show this in some way that fulfills the valence bond theory concept. So we have this sp2 hybridization process where these orbitals get hybridized into a different shape as well as the same energy level, which allows electrons to be separated into different orbitals, providing us with 3 different places where bonds can occur. Methane is sp3, same thing. Sulfur hexafluoride, sp3d2, same thing. We have single bonds, so we're going to have all of those unpaired electrons split apart in those hybridized orbitals. Now, ammonia and water are a little bit different in that we have lone pairs on them. We looked at water previously and saw that it was sp3 hybridized. Ammonia is as well, 1, 2, 3, 4 things attached, sp3 hybridized, but we have to do something with these lone pairs. So we can see that the orbitals are all hybridized. We have a bond here, a bond here, or a bond here, or I should say a location where a bond can occur at all 3 of these locations, these unpaired electrons. This last set of electrons, though, that is our lone pair. Notice that it's part of this hybridized sublevel and hybridized orbitals. Same thing with the water, except we have 2 lone pairs, so we have to show those. By convention, lone pairs have always been shown last, but if that bothers you and you want to put lone pairs first, that's fine. Carbon dioxide and ozone have double bonds, and double bonds are going to be those pi bonds, and pi bonding occurs at unhybridized orbitals. So this goes through sp hybridization. So we have an unpaired electron here, unpaired electron here. We have 2 sites where bonding can occur. These are going to be our sigma bonds. And then we have a p orbital that's unhybridized and another p orbital that's unhybridized. We say they're y and z, provided the plane of which the unhybridized bonding occurs. That is not 100% necessary. It's just additional information to show the 3-dimensional concept of the pi bond or the pi orbitals overlapping. And this is where the pi bonds occur. Where ozone is kind of a combination of both pieces. We have a double bond and a lone pair. It goes through sp2 hybridization, 1, 2, 3 things attached. So we have the sigma bond here, sigma bond here. Those are our unpaired electrons that can do the bonding. And then the lone pair. The lone pair has to be part of the hybridized orbitals. The last bond is in an unhybridized orbital, so we say pz, and that's where the pi bond occurs. Hopefully this was helpful and provides you with additional information about the expectations and simplifies things in a way that makes you more comfortable with what you're going to be seeing on the exam. If you have additional questions, please email me or text me through Mind, and I'll get to them as soon as I can.